In stats, we talk about distribution. So let's see what is a distribution. And in general, a distribution means distribution of something. So distribute, for example, if you're talking about weights or height, they are distributed in certain fashion. So where we can say, for example, in the weights, we can have different categories or classes. So we can have like, for example, 10 kg, 20 kg, 30, and so on. So they are different grades and different. If we talk about a sample, different members which are sampled, they can draw these numbers or values from these different intervals. So if we take these values and we put their frequencies in the shape of a table or in a shape of a graph, we can see their distribution, or we can observe their distribution. So distributions, then they acquire some specific shapes. For example, we have a data here, and it's a data where the buses are arriving late, and that was a concern to the transport company. Maybe they were trying to, not fire, but maybe do some penalties to their drivers. And in this data set, we see the buses, they can be late as 1 minute up to 10 minutes. By the way, they are very sensitive as far as this transportation system is concerned. So we get some numbers. So for example, here in this table, we see that bus number 1 arrives late by 9 minutes, then we have 7, 3, all. And the range is, minimum number we see is 1, maximum is 10. So the range is 10 as far as this data set is concerned. What we can do with this data is, first we can make their frequency table. So we can draw different classes, or we can get different intervals. Here our interval is small, so we are just looking into how many buses are 1 minute late, 2, 3, 4, 5, 6, and so on. So 2 buses are 1 minute late, and then we have 8 buses 3 minutes, and so on. So if we get these frequency tables, we can have an idea about the distribution. So mostly these distributions are such that we can see that most of the buses are like in this category, they are like 3 minutes late. Then some of them we see they are 6 minutes late. So when we plot these things, we can observe, or we can have an idea about the shape of distributions. So this frequency table is obviously representing the distribution, and we can see that in this graph. So here, this distribution looks like something like this. So we have on our x-axis, we have the minutes, and on the y-axis, we plot their frequencies. And then we can infer the general shape of distribution. So this distribution looks like bimodal. So there are 2 modes. Modes are the ones where we have, frequency of occurring most of the values. Here we have 8 numbers, so obviously this is the true mode, but again we can observe a second peak here. So in general, this distribution looks like something like this. We can say looks like a normal distribution. We'll talk about normal distribution in a coming section, but the idea here is to just elaborate what these distributions are. So distributions are where we see how the values are distributed in different classes or groups. Different moments of distributions are these are the parameters or different qualities with which we can talk about these distributions. So for distributions, we have a mean or an average. We can look into the shape of the distribution. Some distributions are skewed, or some distributions are perfectly look like normal or bell shaped. We can talk about their variance, where we have like an estimate of how the values they vary from one to another, and we can look into the kurtosis, which is actually the height of their mod, or the height of these distributions. So these parameters are called as moments of distribution. Okay, so we talk about mean. Let's see what mean is. So mean is the average of the numbers. You might know of it. So average is, as you know, you take all values, get their sum and divide it by the total numbers. We denote population mean with Greek letters and sample mean with these English letters, but a bar on it. A variance is the average of the squared deviations. So we take these deviations and we square them. Why we square them? Because the deviations are actually calculated from the mean. So anything which varies from the mean we take that number and subtract mean from that. So that gives us a deviation. So theoretically, the sum of deviation goes to 0. So that's why we square them and we take their average. So we cannot have the average of deviations since sum of their deviation becomes 0. So that's why we square them. So in this case, when we square them, we get a property or a new parameter which we call it as variance. In this slide, we see the relations or the equations that are used to calculate the variance. So in the top, we have this population variance represented by this sigma square, and sample variance is represented by English letter, as I said, S. So we have S square. And here we have in this equation, in the middle, we have these deviations from the mean for both the population as well as for the sample, where we are squaring them because we know that sum of those deviations is equal to 0. We will do that in an example and it will be elaborated in a short while. Since we sum these deviations, these square deviations, so they are represented by this symbol over here. So where it says I is equal to 1 up till n, how many times, how many numbers you have to do that for each number, and then you in the end you will sum them up. And then you take that answer and divide it by the sample size in case of population, and in case of sample we do n minus 1. That is related to another concept called as degrees of freedom. Why we do n minus 1? Because as per the concept of degrees of freedom, for any sample of the size n, we have n minus 1 degrees of freedom. What it means? It means that we have n minus 1 independent sources of information. You can go and check in the literature about degrees of freedom. Let's do a small example to elaborate that. So for example, if we take our bus data, we have some numbers. So let's take a simple example. We have these up 1 up till 3 minutes. So we have, for example, one bus got 1 minute late, the other got 2, the third got 3. So if we take these values, we can have their mean or y bar, since it's a sample, so we can take y bar, so which is equal to 1 plus 2 plus 3, this is equal to 6, and total numbers are 3, so our mean is 2. We can get these deviations like we can have for first one, it will be like 1 minus 1, 1 minus 2, so that is equal to minus 1. For the second one, it's 2 minus 2, so that is equal to 0, and for the third one, it's 3 minus 2, so that is equal to plus 1. So if we just simply sum them up, minus 1, 0 and 1, that goes to 0. So that's why the sum of deviations is equal to 0. We square them. So if we square them, let's denote this thing with d, and let's denote this thing with d square. So d square here is 1, here it stays as 0, and here is 1. So when we sum them up like in this, so that is equal to 1 plus 1, 2, and then we have our n minus 1, which is the number which we are using to divide that, so that is 2 minus 1. So in the end, we get this variance equal to 1. Okay, since in the variance we square all these deviations, now we want to get the square root out of it. So when we take the variance, it's a squared value. So we want to get the take this square out, so we introduce another parameter over here which we call it as standard deviation. So standard deviation is the square root of the variance. It's the average of squared deviation, which was actually the variance. So it is the square root of the average of the squared deviations. So we take variance and we take the root, then we get the standard deviation. So mainly in our literature we use mean and standard deviation about the distribution. So whenever we talk about the distribution, we say that every distribution has a mean and a standard deviation. Now how can we calculate them? Obviously for those normal distribution, this is the way we do that, but for other distributions there are different formulas. Since I mentioned normal distribution, so let's look into it. A distribution that has a shape like this, that has a shape like a bell, where your right hand side from the middle is equal to the left hand side, or we can say it's symmetric. So any data that is having this kind of distribution is called as a normal distribution. Do the population weights are distributed normally? We can assume that. Is the distribution of the leaves on the plant follows a normal distribution? Most likely. So most of the observations around us these numbers or values are distributed like this normal fashion. If we plot their distribution, they will look like these bell curves. So whenever we have this bell curve, we assume or we suspect that the distribution underlying is a normal distribution. Okay, sometimes distributions are not perfectly normal. They are kind of skewed. So that concept comes over here is skewness. So distributions are, skewed or pulled from symmetric, from normal. So here we have negatively skewed or skewed to the left, where we can see this skewness or we can see this long tail kind of a thing. So whichever tail is pulled, we will use it as a measure to get that skewness. So for example, if we have a long tail towards the left, we say it is skewed to the left. If it is towards the right, we can say it is skewed to the right. And this right skewness is also called as a positively skewed, and this left skewness is also called as a negatively skewed. In case of skewness, the mean, median, and mode, they are not coinciding with one another. In case of normal distribution, they coincide. But here is the situation. The mean is towards the left, and then there is a median and mode in case of a negatively skewed values, negatively skewed distributions, and in positive distributions, the mean is towards where you have those right. So actually we have large numbers towards this end, so they are kind of pulling the means towards them. Same way here we have many small numbers towards this end, so they are kind of pulling the means towards them. Since mean is the average, so obviously mean is towards where we have those skewness. Kurtosis is the measure of pickedness. So mesokurtic, leptokurtic, and platykurtic, these are three scenarios of this kurtosis. So mesokurtic is the normal distribution where the shape is like a bell curve. So if we have more height, it's leptokurtic, and the distribution low is platykurtic if it's flat. These words are derived from some analogies. Obviously, the platypus has a shape like this, which resembles to this distribution, and leptokurtic means long tails. So lepto, if you look into these individuals, like they have long tails, right? These kangaroos. So maybe somebody has seen this arrangement and then give name to these distributions. So distributions with longer tails are leptokurtic. Why they have longer tails? Because they have height or peaks in the middle. So far we have seen here in this section is that we can describe the data using different parameters. We can talk about different moments of distribution, and we can talk about central tendency. What is that? So it is where the middle point of these distributions it lies.